So second to last talk today. I hope this is not too tired yet. So my name is Karl Skucha. I'm the Director of Engineering at Salesforce Einstein. And I'll be presenting together with Yan Yang, who's a lead engineer on this project. And we'll be talking about multi-tenant machine learning pipelines. This is something that we deal with a lot in Salesforce. We have a very heavy amount of multi-tenancy. So I think there's 4 talks by our team at this conference. So I will be giving the first one. So I'll give some overview of Salesforce, why we're doing machine learning at Salesforce, how we're solving problems for our customers. And then I'll give a quick primer on machine learning and on real-time pipelines. Maybe just for a little stretch, how many of you have worked on machine learning before? Great. And maybe left hand, how many of you have worked on real-time data pipelines before? Okay, great. So maybe for calibration, how many of you know what Scala is? Awesome. Gives me a good idea. So I'll go through it sort of quickly, and then Yan will join. He'll talk about what we've built, what we actually built, and what are some considerations into our design process. And then we'll talk about the many things we have left to do. So Salesforce is an enterprise SaaS B2B company. I think I got the order wrong of those things, but basically, like, those are fancy terms for we store data for other companies, many other companies from different industries, different sizes, and we provide them with a service in sort of domains that we're good at. And those domains are sales, service, marketing, a few other things. We call those things clouds. And for example, our Sales Cloud makes salespeople of our customers more efficient by providing them tools to sell better. And Service Cloud powers support centers and so on and so forth. So one thing about our customers is many of them are not tech companies, many of them are small companies, and many of them don't have the resources to hire data scientists and build data science pipelines, especially for their sales and marketing efforts. So this is so as you know, to create a pipeline, you have to hire data engineers to set up data warehouses, to set up ETL systems. You have to hire data scientists to build models, optimize models, and you have to hire a whole team of DevOps engineers to set up the infrastructure and to maintain it. So at Salesforce, we like to say we're building the world's smartest CRM. Our team is building the backend of much of this platform, and really we're trying to take the burden on and do the machine learning for our customers by providing them with out-of-the-box integrated predictive applications. Some examples are, which I'll talk about a little bit today, is predictive lead scoring. So basically this is taking a bunch of potential customers and predicting whether they will become real customers. There's also case classification, which is helping route support tickets to the right person so that the end consumers of our customer will get a better service. And finally, there's a few others, but one exciting one is last week at Dreamforce, we announced Einstein Prediction Builder, which actually allows Salesforce admins to predict any sort of field on any custom data model they have within Salesforce. So far, our team has focused on batch use cases of this platform. Many of our flows run once per hour, but of course, I keep getting harangued. Can you go a little faster? Can you do 30 minutes for my customer? And I say, of course, no, I can't do it, but of course I can. And eventually they convince me that this is really important, and I tell them, sure, you can do 30 minutes. And then, of course, they come back and say, well, can you do 15 minutes? And then I get sweaty. But after much discussion, we eventually do 15 minutes. And then someone comes in and says, well, we have a whole different use case. While a customer is on the phone, we need to predict something. We need actually well under 1 minute, and then, we realize that we have to do something else completely. So before we talk about what we built, I want to give sort of a quick introduction to machine learning and to how we think about going to real time. So let's, and I'll take you through a data set, and this is a data set I will use. So for generating a model, let's take the lead object. Again, this is just a fancy name for a potential customer. And we're trying to predict whether this potential customer becomes a real customer. And the is-converted field is basically an indication of that. False means that they didn't become a customer, true it means they did, and blank means we don't know yet. So in this data set, we have only two interesting columns, title and where the lead came from, the source. Of course, the real lead object at Salesforce has many more fields, but I won't bother you with that. So generally, when we build a model, we take a bunch of historical data. We run it through some ELT process where maybe we put it into a data warehouse or a data lake. I will omit those details, but essentially, what we end up doing is some sort of feature engineering steps. This could be anything from normalizations on numerical features to one-hot encoding on categorical features, or something that requires more domain knowledge. But it's something that was predetermined by our data scientists. And then we go through a model training step where we might train one model, one or more models. We can try different hyperparameters. And we will go through an evaluation where we try to figure out or try to determine whether the best model or the model that we actually was the best is good enough to be deployed, is good enough that it will serve good predictions. And once we're sure it can, then we deploy this model and we have our model. So then for our simple pipeline to serve predictions, let's say that our leads, we get changes from our lead object. In this case, I think Max, who became a director, and Jan is a new lead that we get. And we take this data through the same feature engineering step. And this time we use the model to perform a scoring step on the data. And then we get some scores. And these scores are indicators of maybe probability of conversion or just normalized numbers to help the salespeople use them in their business flow to maybe prioritize the more likely leads or whatever. So one thing I want to mention is this is a really simple pipeline. It's not hard to make faster. The thing that's really simple about it is that all the features come from the payload. Everything that we need to predict the lead comes from the lead object. And it's not really hard to make this process faster. It's, well, not trivial. It's also possible to convert all these components to streaming, and then you have very low latency. Things get more interesting when you add other sources. So for example, our data scientists are clever, and they say, well, actually, we want some data from a different object. We want the number of email replies as a feature. And great, we have this in the activity object. We ELT it into our feature engineering step, but then we notice, oh no, we have to join our lead data with potentially a very, very large activity object. These fact tables tend to be very big, and this is a very expensive process. While it can give us more accurate scores, it's not something that we can easily scale to faster speeds. And of course, this becomes compoundedly worse because most of you probably reply to emails more often than you get promoted. So not only do we have to do this for every change on the lead object, but for every change in the activity object. We have to join it to the entire lead object. Because remember, we need our source and we need our the other features. So as you can see, as we add more sources, for every change in any source, we have to join it to all the other sources. So this becomes computationally difficult to basically do. And even scaling a process with multiple sources to an hourly basis is difficult. So typically the way these problems are solved is you, instead of determining the features when you need to use them, you actually pre-compute them whenever the data comes in. And you cache them in what's typically called a feature store. This is usually a key value store where, for example, if we store them in this way where the lead ID and the feature name are the key, as new data comes in, for simple features, we just update them in the feature store. And for aggregate features, we increment them in the feature store. And this way, we can do our scoring decoupled at any point after, because data is guaranteed to be sort of up to date in the feature store. And as you can see, this only scales linearly with more sources. We just have to do, for n sources, we have to do n times more computation. So then going to streaming, architecturally, this pipeline looks the same. I'm not saying it's trivial to go to streaming, but in general, like if you convert your I/O to streaming and you convert your processes to streaming processes, then this architecture looks pretty similar. So that was my quick overview of what this looks like in the ideal world. Of course, it's not so simple in real life, and even at Salesforce, we have some more considerations. We won't talk about the usual details like data management or compliance or just ETL being hard. We will talk a bit about how to reconcile batch data with real-time data. The data is fundamentally different. Batch data has generally more data in it than real-time. So how do you compute features in the same way? And also, Salesforce has over 100,000 customers. We want to build this for multiple sources, multiple entities, and multiple applications. So how do we deal with the true multi-tenancy of this problem? So with that, Jan will come over, and he'll talk about what we're building so far.
Okay. All right, thank you, Karl. So I will go into some of the architectural components in this system. As the time is limited, I would mostly focus on the feature store and some of the features that actually support it. So to begin with, let's look at the high-level architecture of the Einstein Platform. We have a typical batch pipeline which ingests data in a batch manner, deposits the files into some sort of data lake, and we have separate training and the scoring process to consume this data and generate output. And mirroring that process, we will have a real-time scoring process that is strictly for scoring purpose only. It actually grabs the model file generated in the offline training process, but it ingests data in a streaming fashion and outputs the result back to the end user. As Karl has already illustrated, the feature store in the real-time scoring is pretty critical because it allows you to cache intermediate results and you don't need to do expensive things again and again. So this is an ongoing project, so I would mostly go through some of the considerations and the caveats we have encountered along the way, and some of the things we'd like to do in the future. So before we can delve into the feature store, there is a central pillar in this whole picture that is the common feature definition between the batch training, batch scoring, and the real-time scoring. So this common feature definition is meant to abstract away the process of generating feature from raw data. In a sense, it's trying to address this question. So how do we know features used in training and scoring are generated in exactly the same way? So just to bear with me to take a step back to go through some of the basic definitions. So what is a feature? This is a Wikipedia definition of feature. As Wikipedia always is, it's 100% accurate, but utterly useless. So a more practical, although not strictly, although a little bit less rigorous definition would be that a feature is more like a transformed column in a data set that you will plug directly into training or scoring. There is usually a very wide gap between your raw data and your feature set. And you have to do mundane things like field extraction, data cleansing, and slightly smarter things like feature engineering and transformations. And so in the context of Spark ML, before I go into that, let me just, so our platform uses Optimus Prime library that we built in-house that is built on top of Spark ML. So all our machine learning are partly driven by Spark ML. In the context of Spark ML, if we have a raw file containing a lot of leads, for example. The training process is basically feeding a data frame of the features into a so-called estimator. And the end result of a training would be a transformer, or more likely than not, a sequence of transformers. And the scoring process takes in a similar data frame of objects, in this case needs, and applies these transformers one by one on them to generate a data frame of prediction results, which in this case we call them scores. So as you can see, the input data is of the same type, it's need, but they actually ingest very different type of data. The training process usually generates a huge chunk of historical data with a label on it. So let's say 6 months of data. While transformer, the scoring process actually takes in most recent data, like past 1 hour or past 1 day's data, against which you want to actually make prediction with. So the question is, of course, how do we ensure the feature generation consistency? How do we make sure that exactly the same logic is performed on the raw data to generate the features we need to feed into the 2 different processes? Of course, the idea is simple. We can reuse the code and make sure that this particular part is the same, and we can separate it from the reader that actually reads in the data. But remember that Einstein Platform is meant to be a platform that on top of which users can write their own applications. So we do not want to burden users with this explicit understanding of ensuring the consistencies between the 2 steps. That would mean that we will have to have a very simple and composable API for users to define the feature generation processes. So in Optimus Prime, we actually identify some key features in feature generation. First one is an extract function, which basically takes care of all the dirty jobs and transforming the input data into some intermediate state. But it includes things, it's a simple map function that usually encompasses actions like field extraction, data cleansing, etc. And the meat of the feature definition is an aggregator, which aggregates a particular field of the input data along a particular time horizon. Optimus Prime piggybacks on the Twitter algebra monoid aggregator. So it frames the aggregation in the form of a monoid. So basically, for those of you who are not familiar with algebra, it basically contains methods which allow you to transform the input into intermediate state and reduce the intermediate state and present the intermediate state as a final outcome. The third and last defining feature is an aggregation window over which we actually perform the aggregation. So once we have these 3 things pinned down, we have a unique process of generating features from a particular type of input data. So as an example, here we actually generate a feature which is a total number of activities in the past 7 days. As you can see, that this is a perfectly composable API where we identify the input type, output type, the extract function, the aggregate function, and the window over which we are actually aggregating over it. And similarly, if we want to predict another feature that is the number of conversions in the past 1 day, we can perform exactly the same way, and the APIs look very similar to each other. One critical thing is that at the end of the feature definition, we need to explicitly specify that whether it's a predictor feature or a response feature, which is a label used in training process. Because a common pitfall for beginners in machine learning is that you accidentally include the response feature in your predictors, and you will get like machine learning models with very almost perfect performance, and in real life it's not like, and it doesn't work in real data. So this will ensure that Optimus Prime internally will safeguard against this, and the response feature and any derivative feature out of it will not be able to be used in any predictors. So this common feature definition allows us to abstract away some of the common definition, so what defines a feature. So this will allow us to put feature values actually into the feature store, which Karl has already touched upon a bit. So for feature store, the main purpose, of course, is to cache the features. I would like to touch base on 2 things. First is how do we ensure feature caching in a multi-tenant environment, and 2 is how do we actually make this feature cache avoid recomputation. So multi-tenancy in a key value store environment is fairly straightforward, you would say. All we need to do is put tenant ID in the key and secure the API so that no query can request data from multiple tenants. That's basically the gist of it, and that's 90% of it. In practice, there are still some caveats on top of that, which basically we want to scale up and scale down. What does that mean? So in real life, when you have a multi-tenant application, your clients are usually not very uniform. You will most typically have a few gigantic organizations with a huge amount of data, and a few big organizations, and a long tail of very small organizations with only a handful of data. To handle these different types of load properly, you would need to be careful about your key design and in making sure that, say, single tenant's data is evenly distributed across your entire cluster so that you don't overload a particular node. In this case, we put the record type, record ID, as well as a unique feature ID, which identifies the exact feature into the key, so that even if you have a big tenant, or if you have a tenant with a very big object, it's more or less guaranteed to evenly distribute across your cluster. So that's what I mean by scale up. On the other side, since the isolation is at the software level, for a very small tenant, it may only amount to a few hundred rows in the same table. So we don't need to provision special infrastructure for the small tenants, for very small tenants. And that's what I mean by scale down. So those are some of the important considerations in achieving multi-tenancy. With multi-tenancy taken care of, let's look at the actual usage of the feature store, that is to avoid recomputation. Karl has already touched upon a part of it, that is we key different features by the same key. And I will just slightly reiterate this. For example, this lead feature is keyed by its own ID 5, while the activity feature is keyed not by its own ID, but by the lead ID 5. So that feature store will store 3 features, all of which keyed by 5. And the downstream scoring application, when they present the ID 5, they will get all 3 features together just as if they are coming from the same entity, while in reality they come from 2 different places. Of course, this looks like we are actually outsourcing the shuffling step into an external key value store. The important part, of course, is that we don't have to perform the first stage aggregation over and over again. If this joining is only performed once, this does not actually give us any efficiency gain. But in practice, there are a lot of scenarios where you will have to perform the same join again and again and again, and feature caching will avoid the expensive extraction computations at the first step. So the second area where the feature store will save you computation time is aggregation. We have already talked about aggregation achieved by a monoid aggregator. So I will provide just a very simple and straightforward example. Let's say our feature store contains this data, which is basically the user count of a particular, the count of user activity of a particular user. And while the feature is defined very differently, internally, feature store will keep track of some daily aggregations across a certain horizon. So now when the client actually asks for a feature of a count of last 7 days, the feature store SDK would be able to be smart enough to utilize the common feature definition we defined early to compute on the fly what is the actual aggregated value. And if a new data flows in, the intermediate state will be consumed, will be updated, and when the client requests the same metric again, the feature store SDK would be smart enough to know that there is a sliding window. So November 9th data now falls out of the window, and we should update the count. So this allows us to continuously update the feature store in the context of real-time streaming, where we only have the latest data, and we can cache the intermediate data again continuously, so that every time we query for a particular aggregation, the feature store is able to return it. So of course, this example seems a bit contrived in the sense that it is very specialized for this particular access pattern. there is, of course, this question that what if we need other aggregation windows? That is a problem that we are actively solving, and we have a few ideas floating. One of them is to roll up data in fixed schedules. Basically, we keep daily aggregates up to a certain degree, and then we roll up them into monthly and then yearly aggregates. This way, we can support different aggregate patterns, access patterns like last 7 days, last month, year to date, or last 12 months. Of course, it's not for free. It means that you are actually making the granularity coarser for older data. So the access pattern for older data will become less and less flexible as a price to pay. But most of the common queries you want to use are actually against more recent data. A benefit of this approach is that you limit the size of the intermediate state you want to store in your feature store for each feature. A second idea is to perform exponential weighting, which basically means that you weight more recent data more heavily. And the benefit of this is that if you have aggregation over a very long window, like say all historical averages, if you perform an exponential weighting on your feature, it actually allows you, it doesn't save you time, but it allows you to truncate the window to a very small size without losing too much accuracy, since all the tails are less important now. Apart from feature caching purposes, this kind of weighting is actually quite common for machine learning purposes as well, because in a lot of practical problems, you do want to weigh more recent events more heavily. Of course, there's always counterexamples. So in practice, to handle different types of access and aggregation patterns, we will most likely combine these two together. So that's all most of the points I want to touch upon. Some of the key takeaways, as Karl has already mentioned, that real-time ML pipelines are already hard. It's even harder at Salesforce due to all the multi-tenancy requirements. And the common feature definitions are critical for correctness. If you generate the features differently for your training, for your scoring, and for your real-time scoring, over time, the logic tends to drift apart, and you are actually applying a model that is not applicable to your data. And the multi-tenant isolation has to be incorporated in the design from the very beginning. And by experience, if you have a working application and you want to add multi-tenancy as an afterthought, it usually doesn't work very well. And of course, without saying, you have to maximize this sharing and minimize recomputation. The last point is quite interesting. We found that some boundaries, like the aggregation patterns we allow, has to be set for a real-time application on a generic platform. If you allow client applications to perform arbitrary aggregations, it would be very difficult, if not impossible, to at the same time guarantee the real-time latency performance. So, of course, these are only the things that we have already done and we are currently doing. There are a lot of very interesting and challenging problems on the horizon. First, the top of that is shared infrastructure for super large scale model serving. Currently out there are a few frameworks capable of serving like thousands of machine learning models at real time. But in a truly multi-tenant setting, say if we have 100 applications running on our platform, and we have 10,000 tenants, that will amount to 1 million models. To serve them in real time would be a very big challenge, both in terms of infrastructure and in terms of like software design. Also, with a more systematic way of defining the features and caching the features, it's possible to systematize the heuristics in scoring, which means that we don't have to trigger rescoring every time a feature changes. We can set heuristic rules, say this feature has to be changed by more than 10% before we want to trigger rescoring. This type of heuristics is quite common, but mostly implemented in a very ad hoc way. So a common feature definition and feature caching capability will allow this to become more systematic. And also, we will not be talking about real-time streaming applications if we don't have a streaming data source. And streaming cooperative databases is always a very challenging problem. Change data capture is a very hot topic in a number of SQL and NoSQL databases currently, and it's particularly hard because traditional SQL databases are not designed with this type of capabilities in mind. So there are a lot of interesting and challenging problems. Lastly, we would like to have a feature registry where we can further abstract away our feature definition so that we allow client applications to register their features globally to enhance the discoverability and the shareability of our features. So that's only a very light primer. If you are interested to learn more about the Einstein Platform, we have several talks delve into more depths of different parts of the system. Tomorrow, Matthew will be talking in depth about this Optimus Prime framework, which is heavy lifting all our machine learning workflows. And Thomas will be talking about our execution engine and how we manage to run a huge number of Spark jobs in parallel. On Saturday, Anya will be talking about the DevOps side of things. And Chris and Theo will tell you how to make complex machine learning pipelines easy. And if those are not enough, we are always actively hiring. Thank you. Yes, I guess, any questions? Yes. The first question is, do we measure the performance of the model in production? Yes. One step that I didn't put on the architecture diagram is that we have a specific evaluator that runs to evaluate the performance of the models. It's before deployment for now. After deployment, we have a different set of metrics. Yes, we have a metric system that feedbacks these metrics. Yeah. Sorry? The feature distribution. Sorry, I can.
So, the customers for data sources,
Yeah.
the distribution of features can change over time. You guys actually want to.
So for now, the scoring process is mostly using the latest feature value as well as the aggregator value, right? So we are not actually keeping the history in check, but of course, this is something that if we have global registry of features, we can keep a longer history of features and to track these movements. Yeah.
Question back.
Yes.
Which database, I have two questions. Which database you're using for serving? And also, are you using publishing data structure instead like Optimus Sketch and Pitfall for your aggregation or
Sorry, I didn't get the second part. But the first question is, what database are we using? I assume you are referring to the feature store? Right. Yeah. So for now, we are using Cassandra for the key value store.
Second question was, are you using probabilistic sketch maps, probabilistic data structure that come with algebra, like Optimus Sketch and Pitfall?
For now, we are not using that. Yes, but that's something that, yeah, we're not using it now.
Did I read that the feature store is used only in the scoring and not in model training?
In monitoring?
In model training?
Monitoring, yes. For feature store is only used in scoring because it's mostly meant to achieve the caching purposes, so that you really need to score in a very short time period. Yeah. Oh, okay. 1 second. That will take some time. This one? With the face? That's a face.
This is the pipeline.
Here's the end. Oh. Yeah, this one?
No. Maybe this one.
Yeah, that one. Yeah, that one.
This one? Okay. So this is an example, a simple example of joining two features.
It likes the picture.
try.
Any more questions?
Any more questions? Yes.
So how do you deal with streaming data when data is incomplete? For example, if you have a big batch data, you have one column that you can calculate mean, max, standard deviation. So you can normalize it into like a more distribution and represent it properly because some of the models that requires this. But if you only have real-time data coming in, you cannot have a complete view of your feature.
Yes. So that's where the actual aggregation, intermediate aggregation state comes into play. Of course, we can argue that if we allow us to make the intermediate state arbitrarily complex, we can effectively store the entire history. But that is, of course, something that you don't want to do. So it depends on the exact aggregation. We may need to approximate, we may need to do some exponential weighting and to ignore some of the data and perform the aggregation on the fly over a subset of the history. It all depends on what type of aggregation you want to do. Yeah.
And also, your serving is serving pre-computed scoring, or is serving request of evaluation on the fly. Because you are trying to do machine learning on the real-time data, on real-time.
Yes.
Have almost mean wastage of delay. Are you serving from a pre-computed score, or are you serving some of the models results, prediction results on real time?
That is a prediction result.
Yeah. Prediction result. Then my second follow-up question is that how do you handle your model updates without disrupting your real-time constraint?
Yeah. So for now, we are using simple model update caches. We cache the model in the flow. Yeah. But of course, this in the long term, we need to have a more scalable solution to achieve that. Yeah.
Thank you.
Anything?
Thank you.
Thank you.